Alright folks, here we are in another video looking at now the limit of a function. So this is our first big calculus, or we're getting started with calculus now. So previously in the video we kind of tried to motivate where we're going with this. Now we're starting to get into the nuts and bolts of it. So we're looking at what we call the limit of a function. So if you remember in the last video, we talked about with the tangent and the velocity problems, the idea was to approximate the slope of the tangent line, we looked at slopes of closer and closer secant lines. And this closer and closer idea we understood just by, thinking about, if we just had just a silly example here. If we wanted to estimate the tangent line at that point, we could look at, well, that's probably a pretty good estimate, isn't it? We could look at, pick a different point. Let's say at this point. So we can pick other points along the curve, secant line there, maybe back here, secant line back here, all these examples. And eventually, as we shrink this and get closer and closer to this point in question, moving closer and closer there, we get a better and better approximation in most cases, and that's how we approximate our freehand here as best we can, the tangent line, which, yikes, that wasn't a great, that's maybe a little better. In any case, we talked about the closer and closer idea. This is done using limits, so that's what we want to look at, and we'll be talking about it for a couple days. Okay, so a definition here, limit of a function at a point, something close to a definition, a superformal definition, maybe see section 2.4 for the formal definition. We don't need that for our purposes. We don't really lose anything by not quite being so formal, and we don't maybe face that frustration of being super formal with it. Anyway, the idea is just kind of what we've been talking about with that tangent line problem. So the idea is we want to suppose that f of x is defined for all values near a, and that's the key word there. Near a. It doesn't have to be defined at a. Our notation looks like this: lim for limit, and underneath it we write x, whatever our variable is, the arrow to whatever we're approaching, that value that we're getting closer and closer to as an input to the function. So we write and read this as the limit of f of x as x approaches a. If this gets closer and closer to some number, say L, and we say the limit of f of x as x approaches a is L. We say that if we can make the values of f of x arbitrarily close to L by taking x sufficiently close but not equal to a on both sides. And we'll see what this means graphically in just a second, but this is something not super formal, maybe a little bit more formal than the closer and closer idea. But that's what we've got for something like a definition. Okay, so using that idea, let's look at an example here. We want to determine the limit of the function as x approaches 2. So I want to see what happens as I get closer to 2 in both directions. Maybe I'll use different color here. So I've got blue for my curve. So I'm looking at this, I'm saying, well, as I get closer to 2 this way, closer, 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 from there, there. Looks like it's getting closer and closer to 8. From this side, closer and closer, closer to 2 for the input. And it looks like, sure enough, we're getting closer and closer to 8. We can get arbitrarily close to 8 as we like by picking values of x arbitrarily close but not equal to 2. So just by inspection, we would say here the limit as x approaches 2 of f of x equals 8. So again, get closer and closer to 2. Function values get closer and closer to 8. All right, now this is going to look very, very similar to the next example. So suppose I've got this new function, g of x, piecewise defined function. It's got the same rule as in the previous one, for everywhere except x equals 2. When x equals 2, we say that the function equals 5. So the way we graph this back in our pre-calc days is something kind of like this. So again, we're just like we did before, we're seeing what happens when we get closer and closer to 2 from both sides. Let's pick some x values along the way. Both sides. And it looks like, again, I'm getting closer and closer to looks like 8. And in fact, that is the limit. So I get closer and closer and closer to 2. Not equal to 2, because when we're equal to 2, the limit is the function is 5. We're seeing what happens as we get close to 2, as we approach 2. So the limit as x approaches 2, or x goes to 2, sometimes we say, of our function g of x defined up here is 8. All right, one last one. Again, we got a graph that looks pretty similar. One thing I can tell you here is this guy simplifies, if you like, whatever that means, but it turns out that x minus 2 is a factor of this numerator. And so as long as they aren't 0, which happens when x equals 2, but if x is not 2, then this is not 0. You can cancel numerator, denominator, common factors, and so h of x reduces or simplifies to this for x not equal to 2. When x equals 2, it's not defined. You get 0 over 0. So that graph looks the same as it did in the previous cases. Again, we're seeing what happens as we get closer and closer to 2. So we got these values here on the curve. And it looks like the function values, which are on our vertical, getting closer and closer and closer to 8 again. So again, h of 2 doesn't equal 8, but h of x approaches 8 as x approaches 2. In that limit language, what we say is limit as x goes to 2, or x approaches 2, of h of x is 8. So 3 graphs that looked very, very similar. They're different functions. We've got a similar sort of thing happening. So let's look at a summary here. In all 3 cases, we saw that the limit is 8. Now in the first case, the limit coincided with the function value. F of 2 equaled 8. In the second case, part B, it was not the same as the function value. The limit was 8, but f of 2, it's a different function name. G of 2 was 5. And in the third case, for h of x, h of 2 was not defined. 2 is not in the domain of the function h. So you got the same limit in all 3 cases, but kind of different things going on in the background. In the first case, the limit equaled the function value. That's great. In the second case, the limit exists, but it doesn't equal the function value. In the third case, the limit exists. In all 3 cases, it exists. But in the third case, the function didn't even exist there. And so a key takeaway here is that limits are not the same as function values. When they are, it's nice, but it's not automatic. If they were always the same, then we wouldn't bother with any of this, and we would just evaluate functions at the point in question. But the idea, and what we want to remember, we're looking at this closer and closer behavior. So we're not seeing what happens at an x value or at a particular input. We're seeing what happens as we get closer and closer to that value or that input. One last thing to note here, and then we'll wrap things up. Limits do not always exist. The examples that we had, they did. That's great. It's not always the case. So if the function does not approach a value or approaches a different value from each side, then we say the limit does not exist. So from the left, this side, f of x approaches, remember the function value, that's your output, that's your vertical. From the left, we're getting closer and closer to 6 as x approaches 7. But from the right, f of x approaches 2. As we get closer and closer to 7 from the right, we're getting closer and closer to 2 for an output. So in this case, we would say the limit as x approaches 7 of f of x does not exist. Have to approach the same value from both sides. All right, that's the end of this first part of the first video for this this content. We'll have a second one talking a little bit more about these, what we're meaning here from the left and the right, what we call one-sided limits, and then bring infinity into the picture to see how some things can go on with that.